Global Virtual School student. This is your first year chemistry class. I am Dr. Jadvan, and the topic for today's discussion is Avogadro's number. Students, we are discussing chapter 1 stoichiometry, and today's topic is Avogadro's number. Before this, we have discussed stoichiometry and the mole. Students, one thing is very interesting that this SLO from your curriculum, I have quoted it like third time. Why? Because this curriculum need to know the knowledge of stoichiometry, mole, Avogadro's number, molar volume, etc. So in this SLO, that is the student learning outcome, interpret a balanced chemical equation in terms of interacting moles. So moles we have already discussed. Representative particles. So representative particles means Avogadro's number, mass and molar and volume of the gas at standard temperature and pressure. So today we are going to discuss what is the molar volume, what is Avogadro's number. So Avogadro's number is after the name of the scientist who gave the concept of Avogadro's number. And Avogadro's number, actually this is a value, this is a numerical value. Before going into the detail of Avogadro's number, I am just quick recalling you for like stoichiometry. Stoichiometry, what is stoichiometry? This is the study in which quantities are taken according to the balanced chemical equation. So repeating, balanced chemical equation. So in this today's topic, again and again balanced chemical equation concept will be applied. So stoichiometry basically is applied. And then we discuss the mole. And mole, you know, the atomic mass, molecular mass, ionic mass or formula mass when expressed in grams. So when the mass of the substance is expressed in grams, then this is called the mole. And we have discussed the equation like mole equals to, how to find out the moles, mass in gram divided by molar mass. So if you have given the mass in gram of any substance, atomic substance, molecular substance, the ionic compound or its ions, when we divide it by its molar mass, so you must know the formula of that particular substance, then you can find out the moles with the help of this equation. Mole equals to mass in gram divided by molar mass. So now come to the Avogadro's number. So Avogadro's number is closely related to the mole. Avogadro's number is actually the number of particles. Particles means it can be atoms, it can be molecule, it can be formula unit, it can be ions. So all these species like atom or molecule or formula unit or ion, positive or negative, whatever, these are called the particles. So the number of particles in 1 mole of a substance is called Avogadro's number. So how much these number of particles are in 1 mole? That is 6.023 10 raised power 23. So this is the numerical value of Avogadro's number. So 1 mole of any substance, either it's in atomic form, it's in molecular form, or it's in ionic compound, or it's in the form of ions, positive ion or negative ion. So 1 mole of any substance, they contains number of particles that is equal to 6.023 10 raised power 23, and this is called Avogadro's number. Hopefully this is clear. And 1 mole of any gas, any ideal gas, 1 mole of any ideal gas at standard condition of temperature and pressure, STP, standard temperature and pressure, they occupy a volume of 22.414 decimeter cube, and they contains 1 mole of ideal gas at standard temperature and pressure. They contains number of particles are 6.023 10 raised power 23, and the volume occupied is 22.414 decimeter cube, and this is called the molar volume. And what are the standard conditions of temperature and pressure? Standard temperature is 273 Kelvin, means 0 Celsius, 0 degree Celsius we usually call it, and the pressure is 1 atmosphere. So standard temperature at 273 Kelvin and 1 atmosphere pressure, any ideal gas, it occupies, the volume that it occupies is 22.414 decimeter cube, and in this the number of particles for particular gas are 6.023 10 raised power 23. So this volume occupied is called molar volume and it contains the Avogadro's number. Hopefully this is now clear. What is the relationship between mass, mole and Avogadro's number? In previous lectures we have discussed how to convert the mass into mole. Now mass, mole into Avogadro's number. This is very easy. I have a lot of examples for you. 16 gram of oxygen in the form of atom. So if you take 16 gram of oxygen, this is equal to 1 mole, and 1 mole of oxygen atoms contains 6.023 10 raised by 23 number of atoms of oxygen. This is the example as I have given in the topic of mole. Similarly, if the oxygen is in the form of molecule O2, then 32 gram of oxygen O2 will be equal to 1 mole of O2, and this contains number of particles, Avogadro's number, that is 6.023 10 raised by 23. Again, if you have the water H2O, so 18 gram of H2O, like this, if suppose this is 18 gram of H2O in this is equal to 1 mole, and the number of particles of water molecules in this 18 gram, that will be equal to 6.023 10 raised by 23, and this value 6.023 10 raised by 23 is called Avogadro's number. Similarly, these are all the examples I have taken from the I have already quoted in the topic of moles. So you have a clear concept. Of the relation between mass, mole and Avogadro's number. Similarly, sodium chloride, 58.5 gram of sodium chloride is equal to 1 mole, and it contains 6.023 10 raised by 23 formula units of sodium chloride. So hopefully this is clear. And hydroxyl ion, OH, this is in the form of ion. It can be sodium ion, it can be chloride ion. So 17 gram of hydroxyl ion is equal to 1 mole, and it contains number of ions, that is Avogadro's number. So hopefully now you will be clear about mass, mole and Avogadro's number. If mole is double, like 2 mole, number of particles will be double, Avogadro's will be 2 Avogadro's number. If number of moles are 4, then Avogadro's number will be 4 Na, 4 Avogadro's number. Na is used for Avogadro's number, and A is written in the subscript. But students, when we come to the ionic compound like sodium chloride, the explanation for number of particles is somewhat different. How? For example, in the previous slide, I have taken the 58.5 gram of sodium chloride that make 1 mole of sodium chloride. It contains 6.02 10 to 23 formula units of sodium chloride. This is the condition when sodium chloride is in the form of solid, ionic compound. But when we dissolve the sodium chloride into water, it splits into sodium ion, a positive ion, and a chloride ion, a negative ion. So when this is the Avogadro's number, when it split, it gives the sodium ions Avogadro's number and chloride Avogadro's number. So the number of particles will be changed. In this case, number of particles will be double. So the ionic compound that is splitting into ions, their number of particles will be changed, because ions are considered as particle, atom is considered as particle, molecule is considered as particle. So when sodium chloride is dissolved in water, its number of particles will be changed. Number of particles in this case will be double Avogadro's number. Similarly, if ionic compound is different, for example magnesium chloride, you know, when magnesium chloride dissolved in water, it split into magnesium ion plus 2 charge and 2 chloride with negative 1 ion, negative charge. So how many number of particles will be? Of course it will be 3 times. I have given you this example equation. Magnesium chloride when dissolved in water give 1 magnesium ion and 2 chloride ion. So if this is Avogadro's number, it will be Avogadro's number plus double Avogadro's number. So total will be 3 Avogadro's number. So in case of ionic compound, when you dissolve that in water, the number of particles will be changed, number of particles will be different. Hopefully this is clear. Now how to calculate the number of particles? A simple relation, you know, 1 mole contains 1 Avogadro's number, 2 moles contains 2 Avogadro's number, 3 moles contains 3 Avogadro's number. If moles are like different, like 3.5, 1.5, 6.5, then how you can calculate? That is the formula is given. That is very easy, very simple. Number of particles equals to mole into Avogadro's number, and the value of Avogadro's number, you know, is 6.023. If you are given the moles, then just simple multiply that mole with Avogadro's number, then you can find the number of particles. Number of particles means, again, particles atom, it can be number of atom, it can be number of molecules, it can be number of ions, and it can be number of formula units. So if you have given the mass, if you are not given the mole, then what will you do? First you will convert mole into a mass into mole, and with the help of this formula, mass in gram means known mass in gram divided by molar mass, then multiply with Avogadro's number, then you can find the number of particles. So this is the same form, but they have different form, but this is the same formula for to calculate the number of particles of different species. Here are the questions, short response questions. How many covalent bonds are present? I will solve this. How many molecules? Which contain more atoms? Here comes the question, number of atoms. 1 mole of iron and 1 mole of H2. You know, 1 mole of iron, 1 mole contains Avogadro's number. 1 mole contains Avogadro's number, but here is asked atoms. So 1 iron is 1, so Avogadro's number will be 1, but 1 molecule of hydrogen has 2 hydrogen atoms. So number of atoms in 1 mole of H2 will be double. So you have to clearly look what is the question asked, number of atoms or number of molecules. So give reason that 1 mole of different compounds have different masses but have same number of molecules, because size of atoms, mass of atoms is different, but that is very smaller size. Size do not affect the number of particles or number of moles of the substance. So that's why 1 mole of different compounds, they have different masses but they have same number of molecules. 23 gram of sodium Na and 238 gram of uranium have equal number of atoms in them. Of course, because 23 gram of sodium is equal to 1 mole. 1 mole. And 238 gram, this is the atomic mass of uranium, this is also equal to 1 mole. And 1 mole contains Avogadro's number, so they have the same number of particles. So calculate number of carbon atom in 32 gram of carbon, very simple. Number of carbon atoms, first convert this into moles, 32 divided by 12, then multiply it with Avogadro's number, you will find the answer. How many covalent bonds are present in 9 gram of water? You have to ask about covalent bonds, so you must know the number of covalent bonds in a water formula. You are given a 9 gram of H2O. So first of all, convert this 9 gram into moles of water. 9 divided by 18. 18 is the molar mass of H2O. So this is the mole into Avogadro's number, mass in gram divided by molar mass, that is 9 divided by 18 into Avogadro's number. This will give you the answer. So this is the number of water molecules, but you have asked the covalent bond, and you can see there are 2 covalent bonds, 1 and 2 covalent bond between oxygen hydrogen. So we have this number of water molecules, and 1 water molecule has covalent bonds 2, and 3.0 10 raised by 23 will be, of course, we multiply with 2, then you can find the number of covalent bonds in the water. And hopefully this is clear. Calculate number of carbon atoms in 32 gram of carbon. I have already told you. Mass in gram divided by molar mass multiplied by Avogadro's number. You just simply find the number of carbon atoms. That is very easy. There are two solutions for that. First, keep the formula of mole here, mass in gram divided by molar mass into Avogadro's number. Second solution is first separately find the number of moles like this, moles, then multiply this mole with Avogadro's number. The answer will be the same for both of it. So this is hopefully clear. Now is the mole ratios in stoichiometric calculation. This is very important to understand. Mole ratios. Mole ratios mean the ratio of number of moles of reactant taking part and the number of moles of product that are formed. Here is the example, combustion of propane. So actually how you can find the moles of reactant with the help of other reactant, how you can find the moles of product with the help of reactant, how you can find the mole of product with other product. So basically there are three relations, reactant reactant, reactant product and product product. So with the help of balanced chemical equation we can find their mole ratios. First of all, in this example you can see reactant, this is one reactant, so I am just quoting it as a reactant 1, this as reactant 2, this is the product P1, this is the product P2. So if I increase the them 10 to 10, if it is 1 I increase to 10, if it is 5 I increase to 10. So how the number of reactant, how the moles of reactant and products can be found out. So there are basically three relations. First is reactant and reactant relationship. So here are two reactants. Reactants can be more than 2 or more than 1. So R1, we will discuss the reactants relation. So we have R1 and R2. From balanced chemical equation, this showing when reactant 1 is 1, then reactant 2 is 5. If I increase this, instead of 1, if I increase to 10, then how many reactants of oxygen will be there? So if it is 10, then it will be 5 into 10. How many? This is the 50. Hopefully this is clear. If I increase this to 5, then it will be 5. So this will be 5 into 5, that will be 25. Similarly, if there is other relation is reactant and product relation, I take just a random reactant. You can take R1, you can take R2. So I am just taking R2 to product like P1. Randomly just taking any product. You can take even P2 and find the mole ratio. First from equation. Equation is telling you balanced chemical equation. When reactant 2 is 5 moles, at that time product P1 is 3. When this will be 1, it will be 3 by 5. When this will be 10, again I am changing this to 10. Instead of 5, I am taking 10. So 3 by 5 into 10, 5, 2, and answer will be 6. Okay. The third relation is product and product relation. And here are two products, so I am taking the P1 and P2. P1 ratio P2. First of all, equation, that is the balanced chemical equation, is telling when there are 3 moles of carbon dioxide, then water moles formed are 4. When this is 1, it will be 4 by 3. If I increase this 10, then how many will be moles of H2O? 4 by 3 into 10. 10 multiplied by 4, that is 40, divided by 3, then we have the answer 13.3 moles. So in this way, using balanced chemical equation, you can find if you are a different moles, you have different mass, then convert that into moles, and with the help of mole, you can find other reactant with the help of reactant, product with the help of product, other reactant product with the help of other product. So this is actually the concept of the mole ratio. Hopefully this is clear. Now I will apply this for you on some numerical problem. Methanol burns according to following equation. Methanol burning combustion with oxygen, it gives carbon dioxide and water. If 3.5 moles of methanol are burned in oxygen, first you can see this is the balanced chemical equation. Equation should be balanced. Methanol CH3OH equals to 3.50 moles. And you have to find moles of oxygen are used. So oxygen moles you have to find, and water moles how many are formed you have to find. Very simple. First of all, from balanced chemical equation, you have to find the moles of oxygen with the help of methanol. So keep the methanol on the left side and oxygen on the right side. So from equation showing when there are 2 moles of methanol, then oxygen consumed is 3. When it will be 1, it will be 3 by 2. When it will be 3.50, it will be 3 by 2 multiplied by 3.50. When 3.50 multiplied by 3 divided by 2, then we have the answer 5.25. So 5.25 is moles of oxygen. So when methanol 3.50 consumes, then oxygen consumption is 5.25. Okay. Now you have to find the H2O. Keep this on the right side with the help of methanol CH3OH. From equation, this is the balanced chemical equation. This showing when 2 moles of methanol are used, then water formation is 4 moles. When it will be 1, it will be 4 by 2. When it will be 3.50, it will be 4 by 2 into 3.50. 2 and this answer will be 3.50 multiplied by 2, answer will be 7 moles of H2O. Students, here is very important thing. Even you can find the water formation with the help of oxygen, because now we have the moles of oxygen as well. In that case, answer will be same. It should be same. How? Because when you have the known moles of methanol and oxygen, you can find the mole of product with the help of either oxygen, with the help of either methanol. So just to cross check, I will find for you the moles of water with the help of oxygen, because now we have the moles of oxygen here. Equation is telling you balanced chemical equation. When 3 moles of oxygen are consumed, then water mole formation are 4. When it will be 1, it will be 4 by 3. When oxygen consumption is 5.25, it will be 4 by 3 into 5.25. When you will multiply 5.25 with 4 and divide by 3, then answer will be again 7 moles of H2. So this answer is same as that. So this is very crystal clear that you can find the moles of any product with the help of any non-reactant moles. Similarly, product-product relationship, product-reactant, reactant relationship. Hopefully this is clear now. Our next question is example 1 by 2. This is also to clear the mole ratios concept. Iron can be produced from iron ore. It means iron ore is the reactant and the producing substance is iron. Iron is the product. By reacting the ore with carbon monoxide, it means carbon monoxide is also a reactant. Carbon dioxide is produced as a byproduct. It means carbon dioxide is a product. So you must have known what is the reaction and what is its balanced chemical equation. So this showing iron ore is the reactant, reacting with carbon monoxide producing iron and carbon dioxide. So first of all, balance it. This equation is balance. 1 mole of iron, 3 moles of carbon monoxide, 2 moles of iron production and 3 moles of carbon dioxide. So students, previously we have found the ratio mole ratio. Mole ratio of reactant product and product. But here we have given the mass. Is not it difficult? No, it's not difficult, because you know how to convert the mass into moles. So you have given the mass of iron. This is the mass of iron ore, means Fe2O3, and you are asked the mass of iron. It's very simple. First convert this mass into mole of iron with the help of iron oxide moles. Find the moles of, with the help of this, find the moles of iron and then convert back into its mass of iron. So this is like 3-step numerical. First of all, we have to convert this mass into moles of iron oxide, and you know formula for the mole is equal to mass in gram, that is 425, divided by molar mass of iron oxide, and you know iron mass is 56 and here are 2 iron, Fe2, and oxygen, you know, it's 3O3. One oxygen is 16 and multiplied by 3 it's 48. When you add them all, it is 160. So 425 divided by 160, our answer is its number of moles are 2.65. These are moles of iron oxide. So this is the answer. So we have find out this one. With the help of its mole, find the moles of iron using balanced chemical equation. So second is like, you have to find iron moles with the help of iron oxide. First of all, from equation showing when 1 mole of iron oxide is consumed, then 2 moles of iron are formed. So when these 2.65 are consumed, then how many moles of iron are formed? 2 into 2.65, this is equal to 5.32 moles of iron. So 5.32 moles of iron. So we have cleared this moles of iron, and now convert this mole back into mass. That is very simple. Mole into its molar mass. So you know formula is mole equals to mass in gram divided by molar mass. In case of iron, you know iron moles are this 5.32. Mass in gram you have to calculate, and mass of iron is 56. So 56 will multiplied with this. So mass of iron, that is Fe, will be equal to 56 multiplied by 5.32. Answer will be 297.38 grams of iron. It means when 425 grams of iron ore is consumed, then iron is formed, 297.38 grams are formed. So hopefully this is clear now. Now you have to practice the example 1.3 and 1.4. They are similar to find the mole ratios. It may be start from mass, then convert mass into mole, with the help of mole find the other mole, and then convert them into mass if they are asked about the mass. Now what is molar volume? I have already told you, and just repeating here, 1 mole of any gas at standard temperature and pressure, 273 temperature and 1 atmosphere pressure, occupy a volume of 22.414 decimeter cube. This volume 22.414 decimeter cube is called molar volume, and it contains number of particles, Avogadro's number. So relations are very clear here. If gas is oxygen, so this is particularly for gases. Oxygen, hydrogen, 2 gram equals to 1 mole, This contains Avogadro's number and it occupies volume 32.414 at STP. This is important to write, because if you change the condition, then number of volume occupied will be changed and number of particles will be changed. Similarly, if the oxygen gas O2 32 equals to 1 mole, it contains Avogadro's number and occupy volume 2.414. Similarly, ammonia, similarly nitrogen. So this is actually the relation between mass, mole, Avogadro's number and molar volume. So with the help of this, you can convert mole into molar volume into Avogadro's number into mole, and vice versa. Question: what is relationship between mass and volume of the gas at standard temperature and pressure? So these are the relation. So you can take any example from here. What are representative particles? Students, representative particles means how many number of particles are in 1 mole of gas. Of course, in this previous relation, 1 mole of any gas, it contains number of Avogadro's particles, that is 6.02 10 raised by 23. So you have to give the value here. Even you are asked what are represented particles in 2 moles of gas at standard temperature and pressure. Of course, it will be 2 Na. If it is like 2.5, it will be 2.5 into Na. The answer will be here. So question can be asked in any way. So example is, determine the volume at 2.5 moles of chlorine molecules occupy at standard temperature and pressure. This volume you already know, a relation already know. 1 mole is equals to occupy 22.414 decimeter cube. So how many this mole will occupy? Of course, it will simply multiply with molar volume multiplied with 2.5. So answer will be 56. If this is the 4, then molar volume will multiply with 4. So you can find very easily with the help of this relation. So this is a very strong relation, mass, mole, Avogadro's number, molar volume. If you have a clear concept about these relations like mass, mole, Avogadro's number, molar volume, there is no question that you can't attempt any question. You will attempt any type of question you are asked. So this is very important that you must practice the examples and clear this concept. Question 3, this is like extended response question. What is Avogadro's number? So you have to define the Avogadro's number, you have to give its equation, you have to give its example, and you also give the relationship between mass, mole, Avogadro's number. So this was all about Avogadro's number. It's a relation with mass, mole and molar volume, and we have also calculated mass, mole, their mole ratios, the number of particles. So hopefully this is now clear to you. Our next topic is percentage composition.